welcome back. We're almost done with Lesson 5. The end of Lesson 5, we're going to transition into Lesson 6. Lesson 6 is all about floating point representations, which is an introduction to, I would say, numerical analysis, which we'll get into. What we saw at the last part of the last lesson was that the number 4 over 8 had an infinite binary expansion, and then we'll have this theorem that says, can anybody guess what the proposition is going to say? What type of numbers have an infinite binary expansion?
Type 2?
Yep. Proposition. If y in R yields a finite binary expansion, then, and I guess I should actually write what that looks like, with y equal to like b sub I, b1, b0, dot, b negative 1, b negative f, this thing being exact, then for sure we know y is in Q. So any number that can be written exactly with a finite number of binary bits for sure can be written as a fraction. Moreover, in this case, we can write y as a fraction, some integer over a power of 2. What do I mean by that? What are the only numbers that can be written using a finite decimal expansion, binary expansion? Number whose fractional representation has a power of 2 on the bottom. So 2 to the 0 is a power of 2. That means integers can be written in a finite decimal representation. Immediately when I tell you this, what do you know about the number 9 over 10? No finite decimal representation. What does that binary representation, what does that immediately imply about if I store this in a computer with a finite number of bits, what do you know is going to be true about that number of bits? Can it capture that information exactly? No, which means what? It will be an approximation. The moment that it's an approximation, any numerical computation that I do with that stored number in memory becomes inaccurate. Right? Which means, so this leads us to the conclusion let's study 2 types of numbers. Can you guess which 2 types of numbers we're going to study? Yeah, say it again.
Finite and infinite.
Yeah, and in this case, I kind of want to call them like Q1 and R2. And really I want to call them like type 1 numbers and type 2 numbers. And this is going to be with respect to base 2. Could you guess what type 1 numbers are? Numbers that can be stored exactly using a finite string of bits. What do I know about every single number that can be stored exactly using a finite string of bits? What must be true about it? It has to have a representation of an integer on top and a power of 2 on the bottom. So if I plan to store something, so one of the major things that you're not, many of you I think have an open question, what the fuck is this guy doing? Right? What is he doing?
Breaking my brain.
Yeah. What am I doing? So, claim, the moment we use computers to do things, we're using numerical representations of physical data, right? So the moment that we store a numerical representation of physical data, we transform a number into a string of bits. What did we just learn about when that transformation can be exact? The only way that can be exact, so if I'm doing a physics experiment and I get a measurement that looks like 9 over 4, the moment I know that measurement is 9 over 4 and I want to store it in MATLAB, what do I know about that story? It's going to be exact. However, if I'm doing an experiment and I get a measurement like, I don't know, 0.1, that's an inexact representation, which means when I then do calculations in MATLAB, we've made this claim, you've read articles about this, etc., that we use MATLAB to do calculations, right? And many students, if you're not familiar with this, you might assume like, oh, anytime I calculate with 0.1, I'm going to get exact information because 0.1's an easy number. But what are we learning in this representation about the number 0.1 when we actually store it in MATLAB? It's not exact, which means there is error when I go to calculate that. One of the major questions that we will come to talk about is where do those errors come from, and can I, being conscious of this, write code that helps me avoid catastrophic error? We'll talk more about that down the line, but that's where we're going with this. More importantly, the other place that we're going with this is one of the fundamental problems of the last 70 years is learning how to store numbers in an optimal sense in computers. The entire MATLAB engine, everything MATLAB does, is based on that ability. IEEE 754 format is that ability. Guess what we've done over the last 4 weeks of this class? We've built the structure so that you all by week, 7? So by the end of week 8 probably, you will be converting integers or numbers into IEEE format by hand, and then checking your conversion against MATLAB hexadecimal representation of the bit string that's stored in the corresponding variable. Which means that in this class, you will have mastered the fundamental data type upon which all scientific computation is based. Now, I'm not claiming that's going to teach you how to deal with all the syntax that you need to know in MATLAB. There's a whole documentation for that. But I am claiming that if you're serious about using numerical computation in your future, you now have an introduction to the premier data class for numeric data upon which all other stuff is built. That's what we're doing here. That's why I'm doing this. You're getting, I don't know, in any of your classes, have you learned stuff that was built in 1984? It's pretty cool, right? This stuff came into fruition in 1984. We'll talk more about that as we get to that. Yeah.
I've learned stuff from 1984.
That's awesome. Yeah. I did not in my undergraduate classes, for sure. Okay, so if type 1 numbers are numbers that can be stored exactly using finite string of bits, could you guess what type 2 numbers are?
Numbers that cannot store exactly using a finite number of bits.
Yes, numbers that require an infinite binary representation to be stored exactly. And then I love the way that you said that. Any finite string can only what? Approximate and involves significant or hopefully non-significant errors. Okay. So what I'd love to do now is actually, in my lessons, this material that we're about to cover is called Lesson 6. And it's actually an extension of Lesson 5, which is an introduction to floating point. The whole lesson is an introduction to floating point, but what we're about to do is an extension of fixed point representations. So let's suppose for a second that we have a number that is for sure a type 1 number. What does that mean exactly?
It's a number that can be stored in a finite number of bits.
Yep. So let's take a look at an example of this. Maybe we'll call it example 6.1. You all have told me many times now. Question: can I store this exactly with a finite number of bits?
Yes.
Okay, let me go ahead and do this. So 213. I mean, I would really like to do this by hand, but you all say that the only way that I learn MATLAB is to code in MATLAB, right? 213. So what do we got? Des to bin. 213. So what is that? 1, 1, 0, 1, 0, 1, 0, 1. Is that right? 4, 8, 4, 8. And on the bottom, what do I have? I've got a 1 followed by 4 or 5. Let's see. 0, 1, 2, 3, 4. But really I want 5. So the number of zeros correlates with the corresponding power. So in this situation, this number, I take that thing. Right now the radix is at the end of it in the numerator. And then I move that radix over 1, 2, 3, 4, 5 because I have 5 of them, right? So it would be 110.10101. Okay. So this thing right here, we're going to call this y. The fractional representation of y is going to look like this. This is a math object. So this thing exists in our mind. We're going to introduce something called a programming object, which is a data class used to encode this math object. And in this case, what we're going to do is think about this as an unsigned fixed point binary integer. And then we will encode two things. Do you remember when we were thinking about each of these strings, what we had? We had what we called integer part, and then we had what we called a decimal part, or a fractional part. So the thing that I want to think about this is we're going to think about this as a leading part, and we're going to say that L is equal to the total number of bits in the leading part. Well, what did we say about the total number of bits in the leading part? Well, it was the number of integer bits I plus 1, right? So if, in this case, B2, B1, B0, what would L be in that situation? How many bits is required to encode the leading part identically? 3, right? So in order to get this thing identically here, we would call the leading, actually in the math object, has to have 3 bits. How about the fractional part?
5 bits.
Yeah, in order to get this thing identically in the fractional part, I would have 5 bits. Now, we're going to introduce this general thing. It's a general data class, and yours truly made this up. So I've never seen this notation done. I do, teachers haven't been teaching IEEE format. In fact, I've never seen a teacher do this well, even the teachers that claim to have taught me. So this thing right here, could you guess what type of thing, what object this is? So way back when, we had what we call uint. What was uint? Unsigned integer. Could you guess what u fixed is? Yep, this is an unsigned fixed point number. What base is it in? How did you know it was in base 2? Because the base was written right there. How many bits is dedicated to the leading part? L equals number of bits for leading part. And then could you guess what F represents? Yep. Yeah. I guess I should call it T, right? The cool thing is that the number of bits in the tailing part is equal identically to the number of bits in the fractional part, right? Whereas the integer I marks position, not bit count, right? Yeah, so number of bits in fractional part. Let me ask you this. If I were to determine an F and an L to encode this exactly, what would those values have to be? So if I wanted to encode this data in Math World exactly in MATLAB World, what value of L would I need to choose and what value of F would I need to choose? Yeah, so you're telling me if I stored this in the unsigned fixed integer data class, which MATLAB has not constructed yet, right? 3, 5 of the number 213 divided by 32, the corresponding bit string that I would expect to see would look something like 110.10101. Okay, so what does that say? So if we look at this, how many total bits, notice, so let's note something. What is L plus F in this case? 8. Okay, so let's think about this for a second. Every time we assign a variable in memory, what's the corresponding idea? Somewhere in memory we have this string B0, B1, B2, B3, B4, B5, B6, B7. Each of those things is just a voltage, right? Okay, so what would be the string of voltages for this in particular encoding? 110.10101, except what? When I interpreted what this meant, I would want to introduce through the interpretation a radix right there. So this is what we would call an implicit radix. What do I mean an implicit radix? Am I actually storing where the point is when I write that data into memory? No. Specifically, when I have this unfixed or unsigned fixed integer, this string of bits actually represents what? The number 213, and then the location of the radix is actually indicated by the power of 2 in the denominator. Let me ask you this. What would happen if I changed my approach to look like this? Okay, so yeah, let's go ahead and, so L would be what? 4. F is 4. Total number of bits? Yeah, so M is 8. What does this now look like? 0, 1, 1, 0. 1, 0, 1, 0. And then the question, what happens with this? So this thing is what we call our leading point. This thing right here is what? Yeah, fractional part. It's not overflow. It's not underflow. What is it?
Lost that bit, it's gone.
Yeah. Extra information
Not for hot dogs.
that can't be captured in this data class. So what happens there? What do we do with it? Do we just drop it? Do we round up? Do we round down? Okay, so like today, because we don't have any insights on what the best decision to make is, maybe we say to ourselves, all right, let's go ahead and just drop it. So let's think about this thing as 0110.1010. Notice the moment that we drop that thing, so sometimes people call that a chop. So the algorithm that you're talking about right now is just called chopping. Could you guess why we call it chopping? Reminds me of a good horror movie.
Just cut it off.
Literally just cut the damn thing off, right?
Right.
So claim these two things are no longer exactly equal. Why are they no longer exactly equal? All right. So let me ask you this. What is the error in our data encoding? Okay, so we made this claim. Another way to say this, and why don't we call it absolute error? So let's look at the difference between y and y hat. Well, what was y again? 213 divided by 32. That was the exact version. And what was y hat? Well, y hat was the data representation of y stored in the memory of our particular computer, right? Okay. What would that be? Yeah. So this literally is 1/32. Another way to say that it is 5. Let's see. 1, 2, 3, 4. Which is another way to say 2 to the negative 5th. So whatever calculation we do with this thing, we expect that calculation to have this error associated with it. All right, so let me ask you this. What's another algorithm you could imagine for dealing with information that cannot be represented exactly in a particular data class? So right now, the algorithm that Jean recommended is literally just chop it off, right? What's another way to think about it? Rounding up or down. Could you guess what we would say in rounding? Well, what do we say in rounding for decimals? What's the rule for rounding in decimals? Yeah, so this is where we have to actually do a little bit of thought, right? So let's do a quick recall. recall on rounding in decimals. Okay. Maybe what we should do is we should do an easy version, like, I don't know, like 10 point, forget that. Let's just do 0.4. How would I round 0.4? Yeah, so the rounding, whatever the last bit is, when we round it, this one goes down. So this thing would be rounded as 0.0. What about this one? 0.7. What's that rounded as? 1.0. What's the rule there? Yeah, so 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. For sure, so let's count them. Here's one side, here's the other side. There's 1, 2, 3, 4. If it's in the bottom 4, what do we say? Round down. So this thing right here is a clear round down. What about this one right here? If it's in the top 1, 2, 3, 4, what do we say? Round up. What if it's exactly halfway in between? There's some ambiguity there, right? Do you want to hear a funny story? Coded in MATLAB in IEEE format is round up if the bit before is even and round down if the bit before is odd. So that you're not introducing the same type of error in all of your rounding. So the claim is the bit before is probably a random integer, so just use a rounding thing that is cognizant of that integer, right? But you could either choose to round up or round down, your choice. Okay, but what happens, why did we have 10 choices for the decimal digit at each radix? Why is it the case that we can choose 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 0.10? Where does that come from? It's base 10, right? What happens in base 2?
Well, we got 2 choices.
Well, you got to be a little careful, right?
Got one.
This would be 0.0. This would be 0.1. This would be 1.0. Because 0.1 is 1 over a half, right? So the question is, what do you do when you're halfway in between? 2 choices. One choice is to round up. The other choice is to round down. The funny thing about rounding up or down is that the negatives matter, right? If you're at negative 1.1 and you round down, you would end up at negative 2, right? Because rounding down means going left. Round towards 0, could you guess what round towards 0 means? If you're negative, go up. If you're positive, go down. Round towards infinity, opposite. In any situation, though, whatever choice that we make, so if we chose to round up, what would happen associated? So if I look at y hat, let's suppose that now we're going to use the rounding rule, round up. So when I take u fixed 2 of 4 comma 4 associated with 213 over 32, well, 213 over 32 was this number, right? So it's 0.1010. There's an extra bit of information. What was the claim that we made there? If I use round up, what's going to be stored in data? 0110.10. 1, 1. What's the error there?
Plus 1
But it's a different type of error, right?
was
One of them is a downward error, the other one is an upward error. Okay, so the next question that I have for you yeah, let's take a look at this one. Okay, so here's the next question for you. We'll do these together, and that will be the end of today. All right, so one of the major claims of all three of these data classes that we're about to study right now, these are actually three separate data classes. Why do I say that they're three separate data classes? So let's think about this one for a second. So let's just focus in on this right there. So if we look at that one, if you look at U fixed whatever this thing is, right? Whatever I put into this thing, how many total bits are dedicated to this data class? Yeah, so the leading part has 4, the fractional part has 4. That means M, which is the total number of bits, is L plus F, which is 8. Okay. So let's go ahead and look at what those 8 data bits look like. Right now I'm going to say we're actually going to think about the raw binary string. And then we're going to think about the interpreted binary representation. Okay, so in the raw binary string, how many total binary bits do I have? 8 of them. So literally in this situation, I'm just going to have like, and I'll call the raw one with capitals, and I'll call the interpretive values with lowercase for now because I don't have any compelling reason not to do so. 1, 2, 3, 4, 5, 6, 7, 8. Okay. The moment that I know that 4 of these are dedicated to the leading part and 4 of them are dedicated to the fractional part, what does that then say about these 8 bits? B3, B2, B1, B0, point, B negative 1, negative 2. What's happening there? I mean in the data class, not in my actual. What do we call the thing up front? The most significant bit. that most significant bit correlates with
B7.
B7. The least significant bit correlates with
B0.
B0. What is the absolute smallest number that I can store in this data class?
0.
Yeah, the bit string with that number is 000,000, which correlates with the represented value 000.000, which correlates with the decimal value 0. What is the smallest non-zero number that I can store? Say it again. 1 in the least significant bit. Which is what? 1 over 2 to the 4th, which is 1 over 16. What is the next largest number? So what's the number? So like the smallest number I can store is 0. The least large positive number I can store is 1 over 16. What's the number right next to 1 over 16? In a bit string, it's literally just adding 1 to this thing, right? Which is what? 1 over 8, which is equivalent to saying 2 over 16, which is 1 over 16 plus 1 over 16. How are those related? How do I get from the 1 right before to the 1 up? Add one of the smallest bits. So that means that in this data class, between any two consecutive numbers, what's the delta? What's the thing in between? 1 over 16. What's the absolute largest number that I can store? Okay, so let's go real quick here. There are 8 bits, right? The leading 4 are for an integer part. So in the leading 4, let's see, 2 to the third plus 2 to the second plus 2 to the first plus 2 to the 0, that would be 15. Okay, so here's a claim. This number is going to be 15 plus 15 sixteenths. Another way to write that number is it's going to be 16 minus 1 over 16. Which kind of makes sense because 16 would be 1 followed by 8 zeros, right? And then what I do to get the number right under that in terms of this thing is I'd subtract that, right?
Sorry, why is 15? 15 plus 15 plus 15 over 16 because that's the maximum decimal. So binary. I think binary decimal.
What's the largest value of your integer part in that thing? This would be a great question for office hours. I can spend some time with you on this question. I think we've covered this at least on 2 separate days. Okay. So, crazy thing though. Once I've decided on this, that radix doesn't move. What do I mean that the radix doesn't move? So like, basically the concept is in this fixed point representation, How many total bits do I have? I have 8 bits in this thing. The radix is always stuck where? So that means all data, no matter what type of data that I'm going to represent in that computer, that radix is always going to be here. Okay. If, on the other hand, I chose one of these things, and I'll leave this as I have to write up some problems with you, what would happen in this? The radix would be stuck. So let's go ahead and do this. 1, 2, 3, 4, 5, 6, 7. In this case, the radix is stuck right in the middle. What do we know about epsilon? What's the absolute smallest number that I can store in that? 1 over 16. So not super fine, but certainly way finer than an integer data class, right? But if I committed this to my memory, I would never be able to move that radix around. What happens here? 1, 2, 3, 4, 5, 6, 7. Where's this radix stuck? How many leading bits? How many trailing bits? 6 leading bits. 1, 2, 3, 4, 5, 6. Here's my radix point. What do you know about the absolute smallest number that can be stored there? Smallest positive number, not 0. Okay. What's the largest number that could be stored there? Well, let's see. 1, 2, 4, 8, 16, 32. So it looks like 63.75, right? Let me ask you this. What type of scientists would prefer this encoding? What type of scientists would prefer this encoding? Exact scientists, yeah, that's true. Think about that for a minute. What type of person would like this? Which type of person, what type of work would prefer this? Financial work, perhaps we would say that financial work would be really, really nice here, right? And maybe, it depends on how many bits that like 8 bits is not a lot of bits, right? So it's not the case that maybe if we're counting thousands, that would be a good home finance, like $63,000 is pretty good for a standard American household, right? But from the standpoint of implementing, you might say in financial markets, we don't actually need a ton of decimal representations after that particular thing. You might also say astronomers might prefer this, no? Why might astronomers prefer very, very large integer parts and not worry so much about the fractional parts?
The distances in space are so vast that the loss of data that you get.
Right, the loss of data, if I'm talking about this distance from here to the sun, I don't really care about fractions of a mile, right? I just need as much data that I can get to the front of that number. What type of scientist would abhor this, would really, really not like this representation to be able to capture their data well? Chemists, microbiologists, quantum physicists, for sure, right? Why? Because when they go to encode their data, the most powerful information in their data is not even it's not caught in that grid. Okay, what are you noticing now? So here's a claim. Do you think that every scientist can pay for their own team of engineers to design their own computers? Forget every scientist. Can you pay, I don't know, $1 million for somebody to build you a personal computer that is designed just for your needs?
Yeah.
Okay, I want to know you better. Because there's like a bunch of stuff I want to do with my life that maybe you can help me.
$1 million?
Okay, so let's think about economics. Like, the claim is each of these data points has particular value in specific cases, right? But what's likely to happen if we're going to design a computer? Can we design 50 different versions of data? Yeah, what are we going to do instead?
Average case.
Yeah, so one option would be to do the average case, but the claim is for a whole subset of users that buy that computer, the average case is going to suck. Like for financial markets that are, for astronomers it's going to suck because they don't have big enough numbers. For quantum physicists it's going to suck, right? So the claim is if I fix this point, the moment that I fix that point, I don't have a lot of space of my integers, I don't have a lot of space in my representation, and so it is average, but the fact of the matter is I end up not serving the needs of most of my users, right?
That's what we call it.
Okay, so immediately what happens there is, listen, instead of thinking about this thing as fixed and saying, hey, I'm going to say that only 4 bits are stuck in the integer and only 4 bits are stuck in the fractional part, let me recognize that what I really care about is storing as much information about the number that I'm trying to capture as possible. What does as much information about the number of the number that I'm trying to capture as possible mean? It means that I can always think of a number as some 1 point blah, 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 times some exponent. The moment that I multiply an exponent, I am no longer fixing the position of the radix point, but instead I am letting it float. So the point of fixed point will have, I don't know if I'm going to have you write a data class. Last time I taught this class, I had them write a fixed point data class for themselves. But I do want you to be aware of the concept that 2 things are happening. Number one, fixed points were the initial, so like in the 1960s and 70s, there was a whole like generation of scientists that coded scientific data using fixed point. And eventually what they realized is, fuck, like we are literally failing almost every user that we want, because some users want really big numbers, some users want really small numbers. They're both using our same thing. So in order to deal with that downside, they converged on the concept, well, what if we let our data float? So from the 1970s into the early 1980s, they developed an entire approach to capturing data based on floating point operations. And then there was this guy called Kahan who won what they call the Alan Turing Prize, which is the equivalent of Nobel Prize for computer science. I've studied, yeah. I've stood in the room with that guy. He's really interesting. He has like big mutton chops, got a big belly, does some good research for sure. But in 1984, they published this thing called the IEEE 754 format, upon which all floating point representations are based. What we're about to do, we are now to a place in this class that we understand enough about decimal representations, or excuse me, binary expansions of fractional numbers, and then now we see fixed point. We're quick introduction to fixed point. They're not good enough. The next lesson, the end of lesson 6 and lesson 7, we're actually going to see how floating point representations are made. So what happens in MATLAB when we store numbers, and then at that point we'll ask ourselves, what do we want to do with this information? So I'm going to shut up now. Before I shut up, I want you to do something between now and the time I start talking again. This morning, I had the chance, finally. So let's go applied linear algebra. I have another gift for you, by the way, that I plan to upload hopefully later today. And then engineering 11. So this is new this morning. The draft introduction to the pendulum, and then the drafted MATLAB code. I'd like you to download both of those files, and then this MATLAB code is actually my MATLAB code. This is about 15 to 20 hours of coding over the last 3 weeks. It's yours. Open it and play around with it. We will work through this as a team at the start of our lab session together. So I'll tell you, please download that document. So again, you go down to Lab 3, Draft Introduction to Single Pendulum, Drafted Lab 3 MATLAB Code. Here's the draft introduction. The MATLAB code is in a .zip file. Please download it, open it, take a look at it. When I come back, we'll actually talk about that together as we get into Lab 3. All right? So I will see you at 12:05. We'll talk through this, and then later today you'll get back your tests.